Chapter 24, The Physical Nature of Light. How is a radio like a flashlight? How can microwaves act like rays of light? While these may seem like strange questions, they are not. Radio, microwaves, and light are all three forms of the same kind of wave. They just have different frequencies, like chocolate, vanilla, and strawberry are different flavors of ice cream. The same processes of reflection and refraction work with microwaves as with ordinary light. That is why cell phone towers have funny shaped dishes on them. The dishes act like mirrors and lenses for microwaves that carry cell phone transmissions. Human technology has found uses for almost every frequency of light, including frequencies we cannot see. Light is a form of energy, and in this chapter you will learn about the electromagnetic spectrum and how electromagnetic radiation, including visible light, behaves. Microwave ovens, laptop computer screens, sunglasses, and lasers are all different types of technology that take advantage of the unique properties of the electromagnetic spectrum. Chapter 24, Section 1, The Electromagnetic Spectrum. Common objects can range in size. For example, a rock can be bigger than your fingernail but smaller than a truck. While harder to imagine, the whole range of rock sizes actually includes objects as big as the moon and smaller than a grain of sand. Wavelengths of light also come in a range of sizes. We see the range of wavelengths from red to violet, Roy G. Biv, but this visible light is just a small part of a much larger range of light waves called the electromagnetic spectrum. This section explores the whole spectrum, most of which is used by humans in one way or another. The vocabulary we will use in this chapter is electromagnetic wave, electromagnetic spectrum, radio wave, microwave, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. The objectives are to learn about the relationship among the frequency, energy, and wavelength of light, to learn how the speed of light changes in different materials, and identify the different kinds of electromagnetic waves. Light is an electromagnetic wave. What is an electromagnetic wave? Light is a wave like sound and the ripples on a pond. What is oscillating in a light wave? Imagine you have two magnets. One hangs from a string and the other is in your hand. If you wave the magnet in your hand back and forth, you can make the magnet on the string sway back and forth. How does the oscillation of one magnet get to the other? In Chapter 18, meaning later this semester, you'll learn that magnets create an invisible magnetic field around them. When you move a magnet up and down, you make a wave in the magnetic field. The wave in the magnetic field makes the other magnet move. The frequency of the wave. However, the wave in a magnetic field also keeps traveling outward at the speed of light as an electromagnetic wave. If you could shake your magnet up and down 100 million times per second, or 100 megahertz, you would make an FM radio wave. If you could shake the magnet up and down 450 trillion times per second, you would make waves of red light, as shown in Figure 24.1. Light and radio waves are waves of electromagnetism. Oscillations of electricity or magnetism create electromagnetic waves. Anything that creates an oscillation of electricity or magnetism also creates electromagnetic waves. If you switch electricity on and off repeatedly in a wire, the oscillating electricity makes an electromagnetic wave. This is exactly how radio towers make radio waves. Electric currents oscillate up and down the metal towers and create electromagnetic waves of the right frequency to carry radio signals. Tapping a stick up and down in a puddle makes ripples that spread out from where you tap. Oscillating electric current in a radio tower makes ripples of electricity and magnetism that spread out from the tower at the speed of light as electromagnetic waves. The electromagnetic spectrum. The properties of electromagnetic waves. Like all waves, electromagnetic waves like light have frequency, wavelength, amplitude, which we know as brightness, and speed. Also like other waves, electromagnetic waves carry energy in proportion to their frequency. Shaking a magnet 1 million times per second, 1 megahertz, takes more energy than shaking it once per second, 1 hertz. That is why a 1 megahertz electromagnetic wave has 1,000,000 times more energy than a 1 hertz electromagnetic wave of the same amplitude or brightness. Why visible light is different. Almost all electromagnetic waves are invisible for the same reason you cannot see the magnetic field between two magnets. The exception is visible light. Visible light includes only the electromagnetic waves with the range of energy that can be detected by the human eye. The electromagnetic spectrum. The entire range of electromagnetic waves, including all possible frequencies, is called the electromagnetic spectrum. The electromagnetic spectrum includes radio waves, microwaves, infrared light, ultraviolet, X-rays, and gamma rays. Visible light is a small part of the spectrum in between infrared and ultraviolet light. This diagram is a model of the electromagnetic spectrum. It is showing the different types of radiation along the top. It's showing a picture of the wave below that, and then it has a list of the different places in real life that those different types of electromagnetic waves are used. They have them organized from low energy and low frequency and long wavelength up to high energy, high frequency, and short wavelength. The wavelength and frequency of visible light. Wavelength of light. The wavelength of visible light is very small. For example, waves of orange light have a length of only 0.0000006 meters. That's 6 times 10 to the negative 7 meters. Because wavelengths of light are so small, the wavelengths are given in nanometers. 1 nanometer, abbreviated with nm, is 1 billionth of a meter, which we represent as 10 raised to the negative 9. Figure 24.2 shows the size of a light wave relative to other small things. Thousands of wavelengths of red light could fit on the width of a single hair on your head. Frequency of light. The frequency of light waves is very high. For example, red light has a frequency of 460 trillion, or 460 followed by 12 zeros, cycles per second. To manage these large numbers, units of terahertz, abbreviated with a capital T, Hz, are used to measure light waves. 1 terahertz is a trillion hertz, or 10 raised to the 12th power, or a million megahertz. Wavelength and frequency are inversely related. Wavelength and frequency are inversely related to each other. As frequency increases, wavelength decreases. Red light has a lower frequency and longer wavelength than blue light. Blue light has a higher frequency and shorter wavelength than red light. Energy and color of light. The energy of waves is proportional to frequency. Higher frequency waves have more energy than lower frequency waves. The same is true of light. The higher the frequency of the light, the higher the energy. Since color is related to energy, there is a direct relation between color, frequency, and wavelength. Table 24.1 shows the color, frequency, and wavelength of visible light. The speed of light waves. The speed of light. All electromagnetic waves travel at the same speed in a vacuum, the speed of light, or 3 times 10 to the 8th meters per second. As with other waves, the speed of light is the frequency multiplied by the wavelength. This right here is your first equation in physics. The speed of light, which gives you the relationship between the frequency and the wavelength. C stands for the speed of light, 3 times 10 to the 8th meters per second. F means the frequency, or how often the wave wiggles, which is measured in hertz. And that is the Greek letter lambda, which stands for wavelength, which is measured in meters. We're going to skip over these sections, and you don't need to worry about them until later. Finding the wavelength of light. You can find the wavelength of light from the frequency and the speed. For example, the frequency of red light is 4.6 times 10 to the 14th hertz, symbolized with a capital Hz. If you use the speed of light in a vacuum, 3 times 10 to the 8th meters per second, then the wavelength is 6.5 times 10 to the negative second meters. 3 times 10 to the 8th divided by 4.6 times 10 to the 14th. Use this calculation to find the wavelength of blue-green light in a vacuum. The frequency of blue-green light is 6 times 10 to the 14 hertz. The answer is that blue-green light has a wavelength of 5 times 10 to the negative 7 meters. Low energy electromagnetic waves. What does low energy mean? We classify the energy of electromagnetic waves by comparing it to the energy it takes to remove an electron from an atom. Energy great enough to remove an electron can break the chemical bond that holds molecules together. Low energy waves, like visible light, do not have enough energy to break most chemical bonds. Radio waves. Radio waves are the lowest frequency waves. They have wavelengths that range from kilometers down to tens of centimeters, as shown in figure 24.4. Radio broadcast towers are tall because they need to be 1/4 of the wavelength high to efficiently create the large wavelengths of radio waves. Microwaves. Microwaves range in length from approximately 30 centimeters, about 12 inches, to about 1 millimeter, the thickness of a pencil lead. Cell phones and microwave ovens use microwaves, as shown in figure 24.5. The waves in a microwave oven are tuned to the natural frequency of liquid water molecules. The high intensity of microwaves inside an oven rapidly transfers energy to water molecules in food. Microwaves heat up and cook food by heating water molecules. Infrared waves. Infrared light includes wavelengths from 1 millimeter to about 700 nanometers. Infrared waves are often referred to as radiant heat. Although we cannot see infrared waves, we can feel them with our skin. Heat from the sun comes from infrared waves in sunlight. Visible light. Visible light has wavelengths between 700 and 400 nanometers and includes all the colors of the light, Roy G. Biv, we see when white light is split by a prism. The term light commonly refers to this part of the spectrum. However, any part of the electromagnetic spectrum from radio waves to gamma rays can be considered as light. Earth receives almost the whole spectrum of electromagnetic waves from the sun, including infrared, ultraviolet, and visible light. High-energy electromagnetic waves. Ultraviolet light. Ultraviolet light has a range of wavelengths from 10 to 400 nanometers. Like other forms of high-energy electromagnetic waves, ultraviolet light has enough energy to remove electrons and break chemical bonds. Sunlight contains ultraviolet waves, as shown in figure 24.6. A small amount of ultraviolet radiation is beneficial to humans, but larger amounts cause sunburn, skin cancer, and cataracts. Most ultraviolet light is blocked by ozone in the Earth's upper atmosphere, as shown in figure 24.6 as well. A hole in the Earth's ozone layer is of concern because it allows more ultraviolet light to reach the surface of the planet, creating problems for humans, plants, and animals. X-rays. X-rays are high-frequency waves that are used extensively in medical and manufacturing applications, as shown in figure 24.7. Their wavelength range is from about 10 nanometers to about 1,000th of a nanometer, or 10 trillionths of a meter. When you get a medical X-ray, the film darkens where the bones are because calcium and other elements in your bones absorb the X-rays before they reach the film. X-rays show the extent of an injury, such as a broken bone. Gamma rays. Gamma rays have wavelengths of less than about 10 trillionths of a meter. Gamma rays are generated in nuclear reactions and are used in many medical applications. Gamma rays can push even the inner electrons right out of an atom and completely disrupt chemical bonds. You do not want to be around strong gamma rays without a heavy shield. Questions 1, 2, 4, and 5 in this Chapter 24, Section 1 review are going to be part of your homework.